Okay, in this PowerPoint that talks about relationship or measures of relationship a little bit more, and this is definitely more of a conceptual level, and just a couple things I want you to consider. When we're talking about measures of relationship, covariance or Pearson R, I want you to think about correlation versus causality. So think about this. People who sleep on waterbeds tend to have bad backs. Okay, so do waterbeds cause bad backs, or do people with bad backs buy waterbeds? Right, so just a sort of a simple, silly thing to think about, but it can become really important because whenever a researcher runs a correlation statistic or tries to provide an indication of the relationship between a couple of different variables or lots of different variables, it's really important we remember that we cannot talk about causality. It's not a cause and effect relationship that we're measuring. It's just a relationship. We don't know which one came first. Did the waterbed give the person a bad back, or did they buy a waterbed because they have a bad back? It could go either way. So we're just saying, hey, there's a relationship here. Right? Along those same lines, let's think about this statement. And this is true, documented, researched, using actual accurate data. As the number of churches in a community increases, so does the number of crimes. Okay, so using available data, the Pearson R correlation between these two variables is positive 0.6. So remember back to the last really long, sorry about that, presentation, that Pearson R ranged between -1 and +1, with 0 being no relationship. Okay, remember that? Now, so a Pearson R of 0.6, it's not 0, so there is some type of relationship going on there, but it's not +1, so it's not perfectly positive, but again, not 0, so we have something. Whenever we take our 0.6 and we square it, we end up with 0.36. So you see that R squared, 0.36. So remember, after we square Pearson R, it does become our effect size. So we have a shared variance effect size. So if you want to think about it as a percentage, you can think about that 36 as 36%. So the number of churches in a community can explain or predict 36% of the number of crimes, or vice versa. You could put the crimes first and then the number of churches, because remember, it's just a relationship. It's not one causing the other. It's just a relationship. So that could be kind of a weird result, right? You wouldn't expect crimes to increase with more churches, but we have to consider all of the variables and what else could be happening here, right? So there could be something else, another variable that could be contributing to this relationship, and the answer here is population density. So as a city, a town, a region becomes more populated, you typically have more churches and more crime, but it's just due to population density. So this kind of touches on the issues of research design. So you can think of it as garbage in, garbage out. So, or the kitchen sink method is another way I've heard it described. If you collect enough data and you have enough variables, you'll find a relationship between or among some of it, but what use is it? So when a researcher is deciding what to correlate or what not to correlate, make sure to take into account all of the potential factors that might be contributing to that relationship. Otherwise, you might end up with something like this that looks like there's a relationship, but really there's not. It's population density. Okay. We call these kind of additional variables, we call them spurious variables because they are kind of throwing off the actual relationship. So looking at point 1 there, a variable that accounts for the relationship between 2 or more other variables. And spurious variables limit the ability to make causal statements. Spurious variables need to be controlled for in experimental research. They are quite hard to control for sometimes because sometimes a researcher may not even realize it's a spurious variable until after the research has taken place. So an example of that would be, excuse me, even in a quasi-experimental design. So say you have a quasi-experimental situation, you're comparing 2 different curriculum models. So you select 2 intact groups, which creates your quasi-experimental rather than experimental, because remember, in experimental research, you are able to randomly assign participants to either treatment or control or treatment and comparison. Well, in this case, we can't do that. We have to use existing classrooms. And so we're kind of bumped down a notch automatically to quasi-experimental. But nevertheless, we continue. We implement our 2 different curriculum models, take some before and after data, and conclude that curriculum model B was more effective in raising scores. Now, because we have quasi-experimental, we can begin to talk about cause and effect, right? If you have a correlational research design, you really cannot speak to causation, cause and effect at all. But experimental, absolutely, you can speak in terms of cause and effect. Quasi-experimental, you can sort of begin to describe that potential cause and effect relationship. But the point here I want to make is about a spurious variable. So after the researcher conducted the study and found that method B, or curriculum design B, was more effective, he or she then found out that, unknown to her, Classroom B had the gifted and talented cluster in it. So in this district, students are placed, gifted and talented students are typically placed in one classroom with a teacher that also has that GT certification. On the flip side of that, Classroom A had the special education cluster. The district uses that method to, in their opinion, facilitate co-teaching. So the special education teacher comes into that gen ed classroom, gets to know that teacher, they learn to work well together, they co-teach the material to regular ed and special education students, and the district feels like that's a better model than distributing special ed students to different classrooms and stretching out the special ed teacher and so on and so on. So anyway, all that to say, Classroom A had the special education cluster, Classroom B had the GT cluster. So that's a spurious variable or variables that impacted the outcome that the researcher found. Unfortunately, the researcher did not find out that information until after the study was concluded. But you can kind of, through that example, see how spurious variables can really impact your study. And again, that's a research design type of issue that needs to be thought through at the beginning. And that, that's very simplified, but I think it makes the point clear that we need to make sure, first of all, that we're speaking about correlation research in the right terms, that it's a measure of relationship, not cause and effect. And then also, in whatever type of study we're doing, we need to try to address all of these spurious variables to the best of our ability, knowing it'll never be perfect. We're not in the laboratory where we can control everything, but we need to really do our due diligence to as kind of tightly design our studies as possible. All right, so here are just a few other examples of spurious variables, kind of fun to look at. But if you look on the left, the observed relationship was the amount of ice cream sold and deaths by drowning, right? So strong correlation there. As ice cream sold goes up, so does death by drowning, all right? But the spurious variable there was warm months, right? The season. In the summer, you have more ice cream sold and you have more deaths by drowning. So, I know, it's kind of silly, but funny. The next one, minister's salaries and the price of vodka. So, as salary goes up, vodka price goes up as well. But we have that spurious variable, and that is location, right? Urban areas, prices and salaries tend to be higher. All right, you can see the next one, shoe size and reading performance. As shoe size goes up, so does reading performance. Well, it's because older children tend to have bigger feet, right? Number of doctors in a region and number of people dying from disease. So you could take that information, correlate it, and get a pretty high positive correlation, which would be really strange, right? You would expect if an area has a lot of doctors that you wouldn't have as many people dying from disease. But we have the spurious variable, and that is population density. Okay, so again, just kind of some fun examples, but still trying to make the point of considering as many of those spurious variables as you can. You can account for those statistically sometimes in terms of the analysis that you choose, but the majority of it is just going to come from the way the data is collected and the research and the study is designed. All right. What I want to do now is look at, I'm going to skip over this slide really. I want to point out this final slide because when we talked about correlation coefficients back in another presentation, we talked about how both variables have to be intervally scaled in order for a Pearson R to be conducted. And so that's what this table is really showing you. So if it's like a multiplication table, so you go across and then you go down, and where they meet is the type of correlation. So we were looking at Pearson R, excuse me, which you can see you need interval or ratio data and interval or ratio data. And if you have two intervally scaled or ratio scaled variables, you can calculate a Pearson R. But what if you don't have interval variable? Well, you can still run a correlation. We're just going to call it something else. So say you have two nominal variables. You can still correlate those, but we're going to call it a phi or a Cramer's V. And the interpretation becomes a little bit different. But say you had a gender and a pass-fail on some assessment variable. You could correlate those, but we would not call it a Pearson R anymore. We would call it one of these two. Okay, does that make sense? The point by serial is one that's used a lot in kind of issues of measurement, because you could get the person's overall score and correlate it with whether or not they pass the test. And sometimes that's used in like item discrimination or item difficulty measures. But again, still a correlation, but now it is called a point by serial correlation. All right, so that's the last little bit about correlation coefficients that I wanted to share with you, because I didn't want you to think that there was only the Pearson R. There are lots of others, other variables, other types of correlations you can run other than Pearson R.